Right, today I'm going to be covering the Physics Paper 6, that's the alternative to the practical paper. And this one is from October-November 2016. The paper code is 062561. And this is for the Cambridge International Examinations IGCSE. There we go. Let's begin. Question 1. A student uses a pendulum to determine a value for the acceleration of freefall g. Figure 1.1 and 1.2 show the apparatus. A. On figure 1.1, measure the length L of the pendulum. Okay, so at this point you're really just going to pull out your ruler and measure the length that's marked here, between there and there. So just pull out your ruler and do that. Now, the answer they're actually looking for here is 4.1 centimeters. But when I did it, I got a value of 38 millimeters. So why is it different? Well, because when I printed it off of a PDF, it's resized the image to fit it onto the letter size paper, and you may find something similar. So don't worry too much if you're running through this as a practice and this measurement isn't coming out. To get this right, you just need to be able to use the ruler properly. So don't worry too much about that. And just be aware that it may come out differently, and that's because it may have resized it. So there we go. B. The student adjusts the pendulum until its length L is 50 centimeters. The length L is measured to the center of the bob. Explain briefly how the student avoids a parallax, which is a line of sight error, when measuring the length L. Okay, well what the student's going to need to do is they're going to need to view it from a 90-degree angle or perpendicular to the ruler. There we go. So view from 90-degree angle or perpendicular to the ruler. C. The student displaces the pendulum bob slightly and releases it so that it swings. He measures the time t for 20 complete oscillations of the pendulum. 1. Calculate the period, capital T, of the pendulum, and the period is the time for one complete oscillation. Alright, well, if we have the time for 20, then the time for 1 will be given by the time for 20 divided by 20. There we are. And that will give us a value of 1.39 seconds. Now, look at that. That's three significant figures on the top. The bottom one is 20, but that's actually an integer. 20 complete swings. So I'm going to leave that as three significant figures. My time period is 1.39 seconds. Remember to write in your units there. 2. Measuring the time for a large number of oscillations rather than one oscillation gives a more accurate value for t. Absolutely true. It makes it so that the reaction time has less of an effect. Suggest one practical reason why measuring the time for 200 oscillations rather than 20 oscillations may not be suitable. Well, you probably know yourself, if you've measured 20 oscillations it gets quite tricky to keep count, mostly because you're watching the same thing happen again and again. If you do that for 200 oscillations, you might lose count. Another problem with this is, which is even more likely of course, is that the pendulum will slow down to such a point you can't see it move, so the pendulum might stop. And there we go, we only have to put one down, so I've put down the pendulum may stop. 3. Calculate a value for the time period squared. Okay, well the time period is 1.39 seconds, so it's just that value squared. There we go. Of course, seconds times seconds gives me the unit seconds squared. So the answer, 1.93 seconds squared. So that's 1.93 seconds squared. And of course, remember your unit. 4. Calculate the acceleration of free fall g using the equation g equals 4 pi squared times L divided by t squared. Give your answer to a suitable number of significant figures for this experiment. Okay, so they're going to be paying attention to the number of significant figures we use. First of all, let's write it out. And there we go. So we've got 4 pi squared times 0.5 meters squared divided by 1.93 seconds squared. Well, at the top up here, we've got two significant figures. The bottom down here, we've got three significant figures. So although the answer would give me 10.23 meters seconds negative 2, I should really only use 3 significant figures, so 10.2 meters per second squared. D. The student checks the value of the acceleration of freefall g in a textbook. The value in the book is 9.8 meters per second squared. 1. Suggest a practical reason why the result obtained from the experiment may be different. So, first of all, it's difficult to measure down to the centre of the bob. That's quite a tricky thing to do. Another possibility that would go in here for a practical reason would be the reaction time from the starting and stopping of the stopwatch may create difficulties and errors that carry forward. So there we go. Difficult to measure to the centre of the bob. We only have to put down one practical reason. 2. Suggest 2 improvements to the experiment. Well, I think first one, easiest one, use a fiducial mark, somewhere where it's easy to tell that the pendulum is passing by, so it makes your timing more reliable. In 2, of course, we can increase the number of oscillations. We don't have to go up to 200, we could go to 30. And another possibility would be we could use different lengths for the pendulum and average, but we only have to put in 2, so there we go, there's 2. Use a fiducial mark and increase the number of oscillations. Question 2. A student is investigating the cooling of water. She pours 100 centimeter cubed of hot water into a beaker. 1. Record the temperature θh of the hot water as shown in figure 2.1. Alright, so all we have to do here is read that off the picture of the thermometer there, and if we do that we get a value of 88 degrees Celsius. So remember, put in your units. 2. The student measures the temperature θc of an equal volume of cold water, and there we have θc equals 19 degrees Celsius. Calculate the average temperature θ average using the equation θ average equals θ hot plus θ cold divided by 2. Alright, let's put down our calculations. There we are, so it's 88 degrees Celsius plus 19 degrees Celsius divided by 2, and that gives me 53.5 degrees Celsius. And if you're wondering why I'm giving that to 3 significant figures and not to 2, it's because it's quite a big jump from 53.5 degrees Celsius to 54. And if you're in doubt, leave it as 3 significant figures. B. The student adds the cold water to the hot water. She records the temperature θm of the mixture. And we've got 46 degrees Celsius there. State one precaution that you would take to ensure the temperature readings are as accurate as possible, reliable as possible. Well, I think the most obvious one there is make sure you're reading it at 90 degrees to the scale, so make sure you're reading it perpendicular. There we are. So ensure the reading scale is at 90-degree angle or perpendicular. C. A student is provided with a lid with a hole for the thermometer, some insulating material and 2 elastic bands. In the space below, draw a labelled diagram to show how you would use these items to reduce the loss of thermal energy when the procedure is repeated. Alright, well, I think what we're going to want to do is put the lid on top of the beaker and wrap it up in insulating material, and then probably put the elastic bands around to hold the insulating material next to the beaker. So there we go. I've got a beaker which is wrapped up in insulation. We've got the water inside, we've got thermometer and lid, and the only thing I haven't labelled there is the elastic bands. And there we go. So we've got the elastic bands to hold the insulation close to the beaker as well. That's it. D. Using the improvements shown in your diagram, the student repeats the procedure and obtains these readings. θh is 86. C, the cold water is 20, the average 53, and θm, the measured is 49. Comment whether the improvements made to the apparatus have significantly changed the value of the temperature θm. Use these results to justify your answer. Well, let's look at this, because there are a couple of differences, and it's actually quite important to take note of those. Here, the original temperature for the hot water was 88 degrees Celsius. The cold temperature was 19 degrees Celsius. The average was 53.5 degrees Celsius, and the final measured temperature was 46 degrees Celsius. Okay, so what you can see there, of course, is that the average temperatures are almost exactly the same, and yet the measured temperatures is quite a big difference. The measured temperature of the uninsulated one was 46 degrees Celsius, and the measured temperature of the insulated one was 49 degrees Celsius. So I'd say that's quite a large difference, and that's what I'm going to use to justify. I'm going to quote some of the figures. So let's do that now. So there we go. What I've said is, yes, this has made a large difference in the theta m, the measured value. In the original measurement without insulation, theta m was 46 degrees Celsius. But in the measurement with insulation, theta m is 49 degrees Celsius. And that's comparing both of them together when theta av for both, the average temperature, was approximately equal. 53 degrees Celsius versus 53.5 degrees Celsius. That's very, very close together. So there we go. I would say, yes, it has made a large difference. An important thing to recognise is you could also say, no, it hasn't made a large difference, and then use the numbers to justify that. Or you could say it's too close to go, and use the numbers to justify that. It doesn't matter what your answer actually is, as long as you use the numbers to justify it well. E suggests two conditions that should be kept constant for all parts A to D for this experiment. Well, I think the temperature of the hot water, probably the temperature of the cold water, and room temperature would be three things there. So there we go. Temperature of the hot water is for number one, and second one, the room temperature. If there was three, I would also put the temperature of the cold water. There we go. 3. A student is investigating refraction using a transparent block. Figure 3.1 shows the first stage of the student's ray trace. ABCD is the outline of the transparent block. E is at the centre of AB, and G is at the centre of CD. And there's our diagram there. A. On figure 3.1, draw a line FE to the left of the normal above the outline of the block and at an angle I equals 20 degrees to the normal. Alright, so we have to draw a line 20 degrees from the normal to the left of the normal. There we go. It says above the outline of the block, so that's it. So all we've done is put in an angle of 20 degrees. So as always with this type of question, as you do each part, check it off so you know it's been done. B. The student places a pin P on the line FE at a suitable distance from the block. Right. Okay, well straight away I actually missed a bit there, didn't I? Because I have to draw a line FE. So that means that I should have labelled this top section F. So the student places that pin on the line FE a suitable distance from the block. There is a vertical line L1 drawn on side AB of the block at point E. There is a second vertical line L2 drawn on side CD at point G. Alright, so let's just discuss what that last bit's really saying. It said there's a vertical line L1 drawn on side AB of the block at point E. What that means is on the block itself, they're saying they've drawn a line just there. So it's almost as if they're using this line instead of the pins. And on side DC at point G. There we go. There's another line. So those lines have been drawn in on the block itself. That's what that's actually saying. The student observes the images of L1 and P through side CD of the block. He carefully turns the block to the dashed position. In this position, the vertical line L2 and the images of L1 and P appear one behind the other. Okay. Right, that makes sense. 1. On figure 3.1, mark with a cross X a suitable position for pin P. Alright, so what we want to do first of all is put in where our pin should be. And of course we're going to want to put in a pin nice distance away from the block itself. Now what they're actually saying is when viewed from this eye down here, when the block is turned, and this point moves to there, then it will appear as if all these points are in a row. This point G, which is the line, this point E, which is the line, and the pin F, the pin over by F, which marked X. Okay, now just looking at this question again, it says mark with a cross, which we did, a suitable position for pin P. So let's label this pin as P. There we go. 2. Explain briefly the experimental reason for your choice of position for pin P. Well, the reason I chose that point is it's quite a large distance away from the block, so it gives me greater accuracy. So there we go, large distance from the block gives greater accuracy. On figure 3.1, measure the angle theta and enter it into the first row of table 3.1 on page 10. Alright, so we're measuring this angle here, that one. And when I measured it, I get a value of 19 degrees. So let's just write that into the table. 19 degrees. Units are already up on top. C. The student measures the angle theta between the original position of AB and the new position, AB, as indicated in figure 3.1. He repeats the procedure with the values I equals 30, 40, 50 and 60 degrees, and the readings are shown in the table there. And plot a graph of theta in degrees on the y-axis against I in degrees on the x-axis. Okay, let's do that now. There we go, so I've plotted out the graph. I've got I in degrees on the x-axis and theta in degrees on the y-axis, just like the question states that I need to do. So just as we've been requested to do. So now what I'm going to do is plot these points on the table onto my graph. So there we go, I've plotted the points on the table, and now I'm going to put in a line of best fit. And there we go, so it's directly proportional. D. Determine the gradient G of the graph. Show clearly on the graph how you obtained the necessary information. Right, what this means is draw a big triangle and calculate the gradient. So there we go, I've drawn a large triangle onto the graph. I'm going to use that to calculate the gradient, and I've marked the 3 points that are of interest. Now I'm going to write out my calculation for the gradient. Of course, gradient equals change in y divided by change in x. So there we go, gradient equals change in y divided by change in x, which of course is just 50 minus 0 divided by 50 minus 0, because it goes through the point 50, 50, and it starts off at 0, 0, which gives us a gradient of 1.0. So I've left two significant figures there. Excellent. Question 4. A student is investigating resistors connected in parallel. The following apparatus is available to the student: ammeter, voltmeter, power supply, variable resistor, switch, connecting leads, and a box of identical resistors. Plan an experiment to investigate how the combined resistance of the resistors connected in parallel depends on the number of resistors. You should draw a diagram of the circuit you could use to determine the resistance of the resistors connected in parallel. Explain briefly how you would carry out the investigation. Draw a table or tables with column headings to show how you would display your readings. You are not required to enter any readings into the table. Okay, so basically what we're looking at doing is setting up a circuit to measure the resistance of parallel resistors, identical parallel resistors, and how the number of resistors can have an effect on that. So what we're going to want to do is some form of power supply, variable resistor. There we go. And we're going to want to have a selection of resistors in parallel. We'll start off with 2 and say move up to 6. That will give us, let's put an ammeter in there as well. That will give us a good number of different readings. So we start with 2 and we go all the way up to 6 different resistors. We want to measure the current. We're also going to want to measure the voltage across them. There we go. And yeah, that's the best way to do it. So let's look at this. If this is 2 volts, why wouldn't I just set it up, or even 12 volts, it doesn't matter. If that's a voltage, why wouldn't I just set it up without the variable resistor? Well, as I get more and more resistors in parallel, I may find that it's not 12 volts across here anymore because of some internal resistance. So what I can do is I can play around with the variable resistor to make sure it's always the same voltage across the resistors. Alright, so now what we need to do is draw that up a bit better and set it in a series of steps to make our lives easier. I always recommend drawing a little sketch up at the front so you know what you're doing, so you can help explain how to do your experiment. There we go, so that's just my little sketch. Now I've got a rough idea of what I want to do, and I don't need to worry about it. When it comes to the end, I can cross it out or not, doesn't really matter. Just a little sketch that I've done. So there we go, I've drawn that up a little bit more neatly. What you can do if you want, you can label it, it's absolutely fine, you don't have to because the labels are very clearly defined for electric circuits. Now I've got this beautiful drawing there. The very first thing I'm going to do is I'm going to say set up the equipment as above. So now we've got that, set up the equipment as above. Maybe step 2 will be adjust a variable resistor so there is 2 volts across the resistors in parallel. So there we go. Adjust the power supply and variable resistors so there is 2 volts, 2.0 volts across the resistors in parallel. Next step would be to record the voltage and the current in the table below and then calculate the resistance. The combined resistance, of course, for the parallel section. So there we go. Record the voltage and current and calculate the combined resistance for the resistors in parallel. Record this in the table below along with the number of resistors in parallel. Now, step 4. If we've done that for 2 resistors, we also want to do that for 3, 4, 5 and 6 resistors in parallel. And there we go. Repeat steps 2 and 3 so that you have the results for 2, 3, 4, 5 and 6 resistors in parallel. Okay, now what we'll do, we'll draw out the table that we're going to use. And there we are. So we've got number of resistors in parallel, just an integer, voltage V in volts, current I in amps, and resistance, which is calculated as V over I, and that's in ohms. And then our final point would be just to say you can compare the resistance with the number of resistors in parallel from the table. And that's it. So there we go. You can compare the resistance with the number of resistors in parallel from the table. Question number 5. A student is investigating the extension of a spring. A. Figure 5.1 shows a spring with and without a load attached. Now, first bit we're being asked, tick the distance that shows the extension of the spring when the load is added. There we go. So which one of these shows the actual extension when the load is added? Well, it should be from the same point in the spring, so let's look. A just gives us the whole new length, it's not that. B tells us the distance between 2 different points. Here we're going from the start and we end up down at the base of the end, so it's not B either. C is interesting, it's going from the end here to the end here. So that is showing us the extension, I would certainly go with that one. And D just measures this distance here, which tells us nothing. Okay, so I'm going to go then with the answer C. There we are, a nice straight line goes through 0, 0. That tells us it's directly proportional. So let's move on to the first question. 1. State whether the graph shows that the load and the extension are directly proportional. Excellent, we know the answer to that. Statement, yes they are. So, yes they are directly proportional. How do we know that? Because it travels through the origin, 0, 0. It's a straight line. There we go, so the graph is a straight line graph through the origin. Next, 2. The student determines the graph G, or the gradient, G of the graph line. There we go, and this wonderful pictures there, that wonderful number. There are way too many significant figures. G is numerically equal to a constant K for the spring. Write down the value of the constant K, give your answer to a suitable number of significant figures, and include the unit. Alright, let's go up and look at this graph. Here, I could maybe, if I'm taking a point, I'd say that's 4.0. If I was taking a point down here, I might say 22.5. Maybe it's not really. This last significant figure isn't as significant as you might think. The reason it's not is because I can note to the nearest half of a value, but I don't note to the nearest 0.1. So it's not really three significant figures here. This is two significant figures. Why is that important? Because it's rise over run. So I would have a calculation along those lines. I'd have two significant figures again over something that isn't quite three significant figures. So I'd probably say it's two significant figures there as well, in terms of the way it works. So I would actually say this should be two significant figures for my value, which is, taking this and rewriting it, 0.17. There we go. Alright, there's something else that's missing. The units. What are the units? Let's come back up here. We have millimeters on this one, on the X side. That's millimeters and Newton. So my gradient should be newtons, millimeters to -1. That should be the units. Let's write that in. There we go. So that should be 1 mark for that bit, 1 mark for that bit. Nice. Alright, and that's the end of the exam. Hopefully you find that useful, you find it helpful. If you have, please feel free to like and subscribe. If you want to, please feel free to leave a comment in the comment section below. And you know what, good luck with your exams, and have a great day.